Yeah, so as I have mentioned, we are in week 8. We hope to do week 9, 10, and up to 12. Most likely, of course, the week 13 is general revision, and we might cover that. And I have, as I've been mentioning, you will see a request by the GA to communicate with you so that you can have some number of tutorials, particularly to assist you with the problem solving and examples. So for now, I guess we are doing okay in regard to coverage of the material that we require to cover. So so for now, we start with this material. And as a start, we are going to start discussing the electric potential. And from our discussions in the preceding sections, we can obtain electric field intensity E due to a charge distribution from Coulomb's law in general, or when the charge distribution is symmetric, as we saw in last week, you can be able to obtain the Gauss law. Now, those are two ways in which we can be able to obtain E. Another way in which you can be able to obtain electric field intensity is by using electric scalar potential, in which case we are going to be able to find how in this class. Now, in a sense, this way of finding electric field intensity is easier because it is easier to handle scalars than it is to handle vectors. So we are going to find a way in which we're going to be using the a scalar, the one that you are calling electric scalar potential, V, to determine E. So suppose now to do that, suppose we move a point charge Q from point A to point B in an electric field E as shown in figure 418. I have figure 418 here. And we are saying, suppose you move the point charge from this point A and to point B. So the question is, how would you determine the work done in moving that charge? So for us to be able to evaluate E, that is electric field intensity, we are going to start by determining the amount of work that has been done in moving the charge from that point A to point B. And as usual, those who are following us on YouTube live, be sure to indicate your number and your full names so that your details can be captured that you have attended the class. Okay, so let me just write that for the sake of this. So from Coulomb's law, we know that the force on Q is given by QE, so that the work done in displacing the charge by the elemental length dl is given by minus f dl. And I guess that is something we have already seen. So again, for the sake of getting this point, we can say that you have your point A at that point, you want to move it to point B, and you are saying the displacement is L, but which is made up of many DLs, or rather, when I say many DLs, you actually say you say many integrals of elemental lengths, and therefore you're saying that the work that is done in moving the charge A from point A to point B is simply going to be given by the force times the length, of course, times the length L. But force, as we found out in our earlier classes, is always obtained by the force experienced by the charge Q due to electric field E. And therefore, that is why you are going to find that is going to be given by QE times the length. But since we don't know the length because it is following a line, then you can say that this line is equivalent to dl, but of course from point A, point B, and therefore we are saying that you can say that the total work is going to be given by integral of QE dot dl. E is a vector and L is a vector, and therefore when you do that, you're going to find that is how you obtain the work that is moves the point charge from point A to point B. So of course that is what I have been I have just developed from question 458, and we are saying that you are going to find that the work is going to be expressed with a negative sign, and that negative sign means that the work is done by an external force. It is not the field E that is moving the charge, but rather it is an external force, probably someone holding the charge and pushing it from point A to point B. That external force is the one that is causing us to express the work with a negative sign. So, so having said that, so as you can see, the equation 5.8 we have developed from 4.58 to 4.59. Just as you can see, since Q is not since Q is a scalar, then and it is not dependent on the length, then it comes out of the integral. And now we are saying something that if you divide both sides by Q, it gives the potential energy per unit charge. So in this very simple equation, if you divide by Q and you divide by Q, the Q goes, and then we are saying this is equivalent to V A B, that is potential at point A due to the field at point B, or originating from point B. So that by itself is the definition of the electric scalar potential, as we have just shown. So you're saying that it is given in units of energy per unit charge, and energy is the units for energy is in joules. So and when you have divided by charge, the charge is measured in coulombs. So you have joules per coulomb, and you're going to see shortly that joules per coulomb can also be expressed as volts. So that is now the voltage scalar potential, or electric scalar potential, that simply illustrates the work per unit charge that is performed in moving a unit charge from point A to point B. It is also known as the potential difference between those 2 points. And we are saying that you can define it as you can see in equation 460. Having said that, so there are some points to note that in determining VAB, A is the initial point and B is the final point. So always remember that A is the initial point, which we call as the field. No. It's something that I know I will be saying at some other point, but this is the source point, and the B is the field point. So the field point, we also describe it as the final point or the point of observation. Of course, the point A is where the work is starting. So having said that, we now say that VAB is negative. Here there is, I noticed that the author has some contradiction, which has the potential of confusing you. We're saying that VAB is negative. There is a loss in potential energy in moving Q from A to point B, and this implies that the work is being done by the field. This is just contradictory. And actually, this is actually accurate. When I was going through these notes, I felt like it was contradictory, but I actually think that this is accurate. So I will withdraw that comment that I had made. Scalar, what's happening? Hanging. Okay, it has come back to normal. So I had thought that there was a mistake there, but actually I figured out that there is no mistake. We are saying that in general, that this is how you express the potential, and you're saying that this negative comes by default. It means that it is a potential. But if you now say that if you put a negative on this side, that you have negative, or the result, okay, let me say that. Let's say that you have calculated the V and you have found it to be equal to negative 10 volts. That means that the work is going to be done by the field. Like, okay, let me just give this example. Assume you have a source point Q there, and it has field that is directed outwards, and you are moving up a test charge Q from infinity, this is at infinity, and you are bringing it towards point Q. What you'll figure out is that when you calculate the potential from at point R, at point P, then the potential at point P will be positive, because the work that you have done has created a positive potential. But if you put it, and this is considering that the two charges have the same charge. But if you now realize that by pressing some work here, it was like you are being pushed. Okay, I think I should use some different color. Like if you're now placing a negative charge and this is positive, what will happen is that this test charge will appear like it was already being attracted by the field. And therefore, the potential that will develop will be negative. And that is important, because if the work is being done by the field to bring the charge closer, then an external field will, an external force will appear like it is being pulled, or like being pulled towards the field. And it's like someone, like, just take this example. You have someone here who has a rope, and you are here as another person's, and this person is actually pulling you, and you are resisting, assuming you are resisting. So this is the one I'm calling the external force, and this is now the field itself, E. If the field is pulling you towards itself, that means it has a negative potential. it will achieve a negative potential. It have a negative value. But if this person, or let's say it was a boy, not a girl now, and therefore this boy was being pushed away, but nevertheless he came, then the work that was being done by this field was opposite. He was repairing the person, but the person was still coming. Therefore, the field did a positive work. So that ideally explains the point 2, that is rather not very straightforward, but mentions when the field might be positive and when the field might be negative. And and as we are reading, is that if VAB is negative, then there is a loss in potential in moving Q from A to B. This implies that the work is being done by the field. But when the work is the field is attracting the charge, that means that it is doing a negative work. But on the other hand, if the field is pushing away and someone is pushing back the charge, that means that the field is doing some positive work. And that is what we mean, that if VAB is positive, there is a gain in potential energy in the movement. That is an external agent performs the work. So if we, I think that important is that point is very, very important, and you should actually think about it properly. So if VAB is independent of the path taken, of course, VAB is independent of the path taken. For now, we are saying that we are going to show that later, but we are saying that it is important to know that the diagram that we are talking about here, that we were illustrating the movement. Today my screen is not performing very well. I think I might have overloaded my screen. I will close some windows. So here's the point. I'm saying this, that you are moving your charge from point A, point B. If you follow a straight path, or if you go making some funny drops, but finally you get to this same point, we're saying that the work done is the same. It is irrespective of the path that you have followed in moving the charge from one point to the other. And lastly, if VAB is measured in joules per coulomb, and we have said that that is equivalent to volts. So having said that, I guess we can move on. And we said now that, as an example, if field in figure 418 is due to a point charge Q located at the origin, then the electric field can be expressed as shown in the figure 461. That is something we already found out, that E is always obtained by the source of the field itself, divided by 4 pi epsilon naught r squared. This is in the direction of AR, and this is the same thing I do here. This is my Q, and assume it is pointed towards AR, and therefore, and the distance between the point of observation P and the source of the charge is R. Therefore, we are saying that the field will be equivalent to this equation that I've just written right there. So, and we are saying now, having expressed E as that, therefore we can be able to express VAB by simply replacing E in our equation 460. And we were saying that we had DL, that now DL is becoming, DL was a vector. We are saying that this DL now is equals to DR AR, because it is in the radio direction. In the radio direction, like around the radius. And therefore, since we have that, becomes our AR, and this is our vector that we have defined in equation 461 here. and therefore you can just now work it out. And we know that from our definitions of unit vectors, we said AR dot AR always gives us a 1. So this will go out, will disappear. Then we are going to be left with the equation without those vectors. They are going to be to remain purely as scalars. And what we are now seeing is that, of course, we are referring to the position vectors. The position vector from point A, and the other position vector at point from point B, to point B rather. So when you do that integration, I have tried to simplify it for you right here. You can see that when you integrate 1 over r, which is the only factor that is at the dr, you're going to find that it's equivalent to r power minus 2. And of course, when you integrate that one, you simply add a 1 here. It becomes r power minus 1, and then you bring the result to the denominator. You get this expression. And of course, it is from RA to RB. So it is, you might observe that here I have put RA and RB in the reverse version, because I had here we had the negative. So when you remove the negative from that point, you simply, if you remove this negative, then that means you can reverse the limits of integration, and that is how it comes to this. But then what you observe is that because of this negative that I have introduced that point, that means that you have this negative introduced, which now if you remove it, you are going to find that this now changes to again take the shape that has been observed in vision 462A. It's a bit slightly long process, but it is quite straightforward if you just follow the normal ways we do the integration. And therefore, we are saying that the potential at A due to B is simply the VB minus VA. And you're referring that at V, when we say VB, we are referring to them as absolute potentials, which are considered to have the reference point at infinity. So we are saying that where VB and VA are the potentials or absolute potentials at B and A respectively, and thus potential difference VAB may be regarded as a potential at B with reference to A. And that is very important. That VAB is the potential at B due to or with the difference at A or with due to A. So in problems having point charges, it is customary to choose infinity as reference. That is, we assume that potential at infinity is 0, and therefore VA becomes 0 in this case. And since RA approaches infinity, and of course, you can clearly show how VA becomes 0. This is simply because we are saying that VA is directly proportional to K over R squared. So if this is approaching infinity, then this final equation will simply become 0, and that again is rather straightforward. So when you say that V is equal to 0, then you are saying that V will be given by Q over 4 pi epsilon naught R.